Okay, this question continues on the next 2 pages. So let's go ahead and move on to the next 2 pages. All right, same scenario. Rocket fires its engines, uses 5 meters per second squared for 10 seconds. After this time, the engine shuts off and the rocket freely falls straight down back to the Earth's surface. Draw a graph of the acceleration as a function of time from t equals 0 to t equals 20. Okay, so again, we're going to use a straight edge. And we already talked about this, that it's going to go, for the first 10 seconds, it's going to go 5 meters per second. And then, what's going to happen then? When we cut off our engine, what's our new acceleration? Well, we just talked about it a minute ago, right? That it's going to suddenly be under the influence of gravity only, and that's negative 9.8. Or again, in the AP world, we often say negative 10. And with this level of accuracy, I think that is pretty close there. So this is our graph of the acceleration. It's going 5 meters per second squared upward, and then suddenly they turn off, and now it's going negative 10 meters per second squared as an acceleration. I forgot to mention, I went ahead and labeled my y-axis, so I knew I was going to get to negative 10, so I just counted by 2, 4, 6, 8 like that. So we got up to 10 here and down to 10 here. Because in this next graph, again, we talked about a second ago that we've done part of this already, right? So let's go ahead and graph the part that we've done. So we did this, the increments are a little bit different, so the slope looks different, but it's actually the same slope, it's just the increments are different. So it went up 5 over 1, up 5 over 1, up 5 over 1, etc. for the first 10 seconds. Then, at 10 seconds, then what happens? Well, then it's under the acceleration due to gravity. And so that acceleration we're talking about is gravity, negative 10 meters per second squared. And so from this point, we need to draw a line that has a slope of down 10 over 1, down 10 over 1, and down 10 over 1, etc. Okay, so a slope of negative 10 over 1 could also be expressed as negative 50 over 5 or negative 100 over 10. So that's what I did. I went down 50 and over 5, down 50 and over 5. Okay, last page. Using the kinematics equation, this is the equation from the equation sheet, a classmate writes out the following solution to find the time when the rocket lands back on Earth. Explain in one sentence using terms such as acceleration, velocity, position, constant, changing, and zero, why the solution below is incorrect. Okay, let's look at what they did. This is the final y, the initial y. So it goes up and it comes back down. So the initial and the final y's are both at 0. The initial velocity also at 0 because, again, it gets launched up and it starts at 0. And the acceleration is 5 meters per second squared times time squared. Okay, what is wrong with this equation? Well, the problem lies right here with this acceleration. They say the acceleration is 5 meters per second squared. Well, that is true for part of the journey, right? It's going up at 5 meters per second squared, and then the engines turn off, and it continues to float upward, but at this point, while it's floating, so this acceleration is 5 meters per second squared. And then here, the acceleration is negative 9.8 or negative 10 meters per second squared. And so they're assuming the whole time it is 5 when it's not. So this is not correct. Let's take a look at how they worded their answer. The student is assuming that the acceleration is constant. That's what we talked about, that this acceleration was constant for the entire time and does not include the free fall portion of the motion. Okay, they stopped there. One thing when you are answering AP questions is you want to answer the question, and they gave you these words, so you want to make sure that you include some of these words, but you also don't want to go beyond what they ask you. Because a couple things, if you go beyond what they ask you, number one, you could start getting into territory where you don't really know what you're talking about. And if you don't know what you're talking about and you start writing stuff, you will lose points. So they do take off points if you start writing a bunch of baloney. So let's just they use the word acceleration just like they did here. Constant is there. Free fall, not sure if that was one of them, but that's an important part. So they've included some of those words. And again, the main problem being that 5. And so if you were going to calculate this problem, if in any circumstance you might need to do that, what I would do is I would do a calculation for phase 1 while the rocket is going at 5 meters per second squared, and then I would do another calculation for phase 2 when the rocket has the acceleration of negative 9.8 or negative 10 meters per second squared. So I would calculate both of them and then add those two together, because that's what it's a two-stage thing, right? It gets shot up and then it's floating up and then it stops and then it comes back down, right? So it's actually 3 phases altogether, but you would have to break it up according to your information. Part D, from your velocity time graph in Part B, so we'll have to go back and look at that, determine the time when the rocket reaches its maximum height. So let's go take a look at the graph. Okay, here's the graph they're talking about. They want to know, when does the rocket hit its maximum height? What time does it hit its maximum height? So what's going on here? One thing is, some people might be tempted to say it's right here. That's at that 10-second mark. It's the tallest point in the graph. That's the wrong answer. Don't say that. We already talked about what's going to happen. Remember, it goes up for those 10 seconds. They shut it off, and it continues to kind of float upwards. So that is not the max height at this point. All right, what's happening here? Well, we've talked about that's the acceleration due to gravity. So that's negative 9.8 or negative 10. What's happening is it's slowing down. So it's slowing down all the way. Remember, this is velocity. It's slowing down until here. And at that point, its velocity is 0. As far as the motion of this rocket, where is that? The velocity is 0 at the top of its flight. And then it's going to start to fall down, right? So this is where the velocity is 0. That is where the top of the flight is. And so if I erase all my stuff so we can see it, that is at the 15-second mark. So again, the answer there is 15 seconds. Determine how you determined your answer. Explain how you determined your answer. Once again, I'm going to go to what they wrote down, but we just went over it. We explained it a second ago. Okay, the rocket continues upward until it reaches a velocity of 0 meters per second. The slope of the velocity versus time graph is 5 meters per second for the first 10 seconds, and then negative 10 meters per second after that. The velocity time graph crosses the horizontal axis at t equals 15. T equals 15 seconds is where the velocity changes direction. Okay, one last question. Make a claim about the numerical value of the rocket's maximum height. Can we find that maximum height? Right, we're looking for a delta y, basically. Once again, we could do it with equations, but we can also do it with the graph. So let's go back and look at the graph. So we said a minute ago that this is where the launch is, and then it cuts off the engine, and it starts to fall down. And right here at 15 seconds is when the top height, the height of its trajectory is. So it gets launched up with the acceleration, it kind of floats upward, and then it starts to come down. So this at here is the 15-second mark, and that is the highest it goes. Okay, how high does it go at that point? Well, once again, there are equations we could use, but we can also look at the graph. This is a velocity time graph. Anytime we look at a graph, we ought to be thinking about slope and area. A slope of velocity time graph is going to be meters per second. That is acceleration. So if I find the slope of this, that's my acceleration. That's why this is 5 meters per second squared, and this is negative 10 meters per second squared. Okay, so that's not giving us distance. We want some kind of height here. Well, what would the area give us? Area is length times height. And area, meters per second, times seconds, that is meters. That is what we're looking for. So we need to find the area during this part, because that's the highest part. We don't care about this part. It's going to get back to the ground at that point. But here we need to find the area. So the area of this triangle is 1/2 base times height. So its area is 1/2 15 seconds times 50 meters per second. So the max height is 375 meters. Okay, how did we come up with that answer? Evidence. What physical feature of the velocity time graph supports your claim? So we looked at the area. Area is meters per second times second, so that's meters. So we found the area under the curve, and that gave us 375 meters. Once again, let's just look at what they said. They said 375 meters, just like we did. The area under the velocity time graph is equal to the displacement of the rocket. At 15 seconds, the height is 375 meters. They didn't write it out, but if you wanted to go in and write that in there of what we had for our equation, that would help your case. You don't have to, but that would help it. Okay, so as I mentioned before, there are bits and pieces of this question that will help you to do well on a certain free response question that might show up on the quiz.